Welcome back. In our last video, we discussed on the concept of differentiability. We defined what differentiability is. We gave the epsilon delta definition, and we also started off with an example on differentiability. We were to discuss the differential of the function 4x plus y plus I into minus x plus 4y. We already started the process and broke down the first principle definition for the differential before we then proceed to find the limits. So in this video, we will be continuing along those lines and then proceed to find the limits across the different axes so as to evaluate if indeed the differential exists. If you are wondering where we got this concept, which of course comes from the question, please make sure to take a pause, watch our previous video so that you have clarity on what we did to get to this point before then continuing with this. Now, in order to evaluate, of course, we have to take the limits. In order to do this, what we would first and foremost do is we would evaluate the limits across different directions before we then conclude that we have the fact that the limit is unique, which would then mean that the differential will exist. So first and foremost, we will evaluate this along the real axis. Now, if we evaluate along the real axis, of course, that would mean that y will be equal to 0, which would in turn mean that the differential of y would be 0. Now, in this case, it means that we could make that substitution on the first principle such that we will now have that the z, which would of course be the first differential of f, in this case, will now be the limit as delta x tends to 0, which would now be, what will be left here, we have 4 delta x minus I delta x divided by delta x, which in turn would mean we are taking the limit as delta x tends to 0 of 4 minus I, because delta x would factorize out of the numerator, thereby dividing the denominator. So in this case, you would have that your final result will be 4 minus I along the real axis. Now, we have already gotten an answer for the limit, which means along the other axis we want to find, we must be also getting the same answers. Because remember, the limit of a function is a unique value. So since we have already gotten the limit to be 4 minus I along the real axis, we expect that along the imaginary axis or along the straight line, the value of the limit should remain the same. That and only that will let us know that the differential is of course in existence. So now let's see if that is true. Now if we evaluate along the imaginary axis, this would mean that x is of course equal to 0, which would in turn mean that delta x would of course also be equal to 0. So the z in this case will now be the limit as delta y in this case tends to 0 of what will be left from here when we evaluate at this coordinate point. We would have that we're left with delta y plus 4I delta y, right? All divided, of course, by I delta y. And of course, this will work such that if we were to factorize delta y out, we'll have limit as delta y tends to 0 of our function will now remain 1 plus 4I divided by I. And of course, if we evaluate the limit, this is of course going to be 1 plus 4I divided by I. Now, we are dividing by I, which means we can of course rationalize. And if we do so, that will mean multiplying by I over I, such that simplifying this, I times I gives us I squared, which is of course minus 1, remember. And then in the numerator, we would have minus 4 plus I. So if you have minus 4 plus I divided by minus 1, what would you have? In essence, you're going to have minus 4 plus I divided by minus 1, such that in this case, you'll be left with 4 minus I. So in this case, we have gotten the same thing along the imaginary axis as we did along the real axis. Now, Let us evaluate what happens along a straight line. Now remember, for a straight line, we have this to mean that y will be equal to mx plus c. That is, of course, the arbitrary straight line. Now you could decide to be a little bit relaxed in your approach and evaluate along a very, very simple straight line, let's say y equal to x. But then you could also evaluate along y equal to mx plus c and see if your answer really matches. That, of course, depends on you. Now, if we decide to evaluate along the simple straight line y equal to x, then in this case, delta y will be equal to delta x. That is what this would mean. Such that in this regard, we will now have that for our limit, we'll be having that df dz. This time around, remember, we have to evaluate the limit because both sides of the function still remains. It means we are going to be evaluating as delta x tends to 0 and then delta y tends to 0, or you can say as delta z tends to 0. Anyone is fine. Now in this case, the top will not vanish, the bottom will also not vanish. However, delta y is equal to delta x, so you can use this to make a substitution such that all the parameters come together. Now if we make a substitution for delta y, changing all delta y to delta x, we will have that this form will now give us 4 delta x plus, we were supposed to have delta y, but this time around we will now have delta x because delta y equals delta x. And then we have minus I delta x plus 4i delta x, divided, of course, by delta x plus I delta x. This is what we are going to have. Such that in this regard, since delta y has vanished, we can just omit the limit, but we won't. We'll just leave it as it is. So in this case, because delta y is equal to delta x, so delta x being here is enough. Now we'll just leave it for one more line. So in this case, we're going to have 5 delta x plus 3i delta x. Of course, this will be divided by delta x plus I delta x. This is what we're going to have. Now, in this regard, we can factorize out the delta x as it is. In this regard, we'll be left with 5 plus 3i divided by 1 plus I. So we are left with a complex number, which, of course, can be rationalized. So if we rationalize this by multiplying by its conjugate, we have 1 minus I divided by 1 minus I. Now, the multiplication of this on the top will give us 5 minus 5i plus 3i minus 3i squared. And then on the denominator, the multiplication of these two, which are conjugates, will give us a difference of 2 squares. So we're going to have that to be 1 squared minus I squared. Such that if this is simplified, on the top, I squared is minus 1, so 3i squared is minus 3 times minus 1, that's plus 3. That gives us 8 on the top minus 2i. And then at the bottom, I squared is minus 1, that gives us plus 1 in total. Then plus another 1, that's going to give us 2. So, of course, 8 minus 2i divided by 2, that, of course, gives us 4 minus I. So what are we seeing? We have seen that along the real axis, along the imaginary axis, and along the straight line, the value of the limit remains the same. So if this is the case, it means that we can say that the differential of the function is indeed 4 minus I. So thus, we can say that the differential of the function in this case is indeed 4 minus I. And that ends the question. So you can see, as far as this is concerned, when we explore the differential, the most important thing to always do is, first and foremost, what is a differential limit, or what's the limit value along all the possible axes that we can consider? Usually the real axis, the imaginary axis, and along the straight line. Remember, we taking y equal to x is just for us to take the simplest possible version of the straight line. In practice, you could decide to use another version of the straight line. Let's say y equal to 2x. Let's say y equal to mx plus c, where you are also adding in the y-intercept where possible. All of those are very, very valid versions of the straight line, right? So this shows us how we can discuss the differential of the complex function. As always, make sure to watch through the video. You can also go through the last video, the previous one to this, to also see how we also started the question. Please make sure to like, share, and subscribe. Share to your colleagues so that they can get to see this example, and then turn on your notifications so you do not miss any of our next videos.